pleasure to introduce a friend and good colleague for what, 20 years or so, Guram Bezhanishvili. He is currently at New Mexico State University, but also visiting us, and a current member of CCAT at Chapman University, and we hope that that will become a permanent arrangement very soon. So that's a work in progress right now, but we're really looking forward to that. And he's already fully embedded into the program, talking with even our undergraduates and our graduates and everything else. So it's been really a good collaboration, even in just brief few weeks that he's been here. So Guram is going to talk to us about something that I didn't know that he had a specialty in. So this is going to be quite interesting.
Quite a few of those.
Yeah. Finding something he's not interested
That's
in.
exactly.
Right. So, Guram will be talking to us about the Gödel translation, some history in new directions. Thanks, Guram.
Thank you. Thank you, Drew. Thank you for nice words. It's a pleasure to be here. And yesterday I had Marco arranged a 1-hour meeting with some of the students. Some of them are here. Most of them had enough already yesterday. So for those who are here, a couple of first slides will repeat because I need to set up the scene. Like Drew said, this is about Gödel's translation, and there's a lot of history behind it. And some of this we discussed yesterday, but like I said, I'm gonna repeat myself. So things started maybe even before Brouwer, but Brouwer was the very colloquial proponent of not accepting the law of exclusion. Right? And here's his picture, and here's Hilbert's reaction to Brouwer. And that resulted in a real fight between the two. And in spite of the fact that Hilbert never accepted intuitionism, other people started to take notice. And here are some of the directions that came out of it. Early on, we're talking about 1920s, right? So Heyting was the first, who axiomatized the ideas that Brouwer had. It remains mystery to this day whether Brouwer accepted Hilbert's axiomatization.
Heyting's
axiomatization. But the rest of the world did. And Heyting actually won Dutch Mathematicians Award in 1926 for his paper. So then this famous BHK interpretation came about. And it's very important, for example, how implication is interpreted, right? That intuitionists accept that an implication is proven, provided they can transform a proof of phi into a proof of psi. And then Glivenko's famous double negation translation, which was further developed by Gödel and Gentzen, came about, which actually showed very close connection between intuitionistic logic, classical logic, and negated statements. And as an aside, I want to mention that it is this construction that plays also a very important role in poetry topology. And these were some of the developments at the time. And there's another translation that I'll concentrate on, right? So these are not the developments that we'll be talking about. What we'll be talking about is the translation that Gödel came up with in 1933, when he tried to understand intuitionistic logic from the perspective of modal logic.
And why he made it is a strange attempt?
Why he wanted to?
Yeah.
Because at the time, people were thinking about what kind of new beast this intuitionistic logic is, right? So they wanted to try to study it from different perspectives, right? And one perspective of the time was actually modal logic and how it relates to modal logic, how it relates to classical logic. That's what Glivenko did, and also Gödel was involved in it, right? They also wanted to understand, how it relates to other things. And very soon, you will see that there's semantically, there's very good reason to interpret intuitions modal logic, right? And I want to point out that, so let me mention the syntax. Yeah, okay, so let's talk a little bit about what Gödel did, right? So there was this, the study of modalities goes way back to Aristotle, right? But it wasn't until the beginning of the 20th century, because of the work of Lewis, that modal logic became, you know, a very formally studied part of logic. And this was in relation to studying these paradoxes of material implication. And modality was used, you know, Lewis used this modality, you know, to present this, what he called strict implication calculus. And for that, this necessity operator was made. And using this necessity operator, this is the syntactic side of the Gödel translation. So what Gödel does is that he boxes every formula, right? And here's how he reads implication. Right? Now, one good reading is to read box as it is necessary. So then intuitionistic implication can be read as it is necessary that classical field implies style. Or you can read it as it's provable. You can read box as provable. And then you read the implication that intuitionistic implication means that it's provable in some formal system that phi implies. But this is all the syntactic side, right? And now I want to I'm going to go now to the semantic side. And what I'm going to use, this is going to be the main theme of today, right? That I'm going to show you how topology is going to be the uniting theme behind all these connections, right? And there's going to be a very interesting quote that I'll let you chew on in a little bit that Rasiola and Sikorsky made back in the 60s in their famous monograph, you know, and I think that that's really the perspective that will be pushed, you know, throughout the first half of the talk, which is mainly going to set the scene and provide these classic results on which we're going to build on and get to the modern state of where we at with this thing. So semantically, you know, what is the difference between classical logic and intuitionistic logic? Think of classical logic as Boolean algebras, and then typical examples are power sets. That's something that Drew and I were talking to undergraduate students earlier today. And then, you know, there's this famous Stone's representation theorem that actually represents every Boolean algebra as a power set algebra, as a subalgebra of a power set algebra. And then it's very easy to see why the law of excluded middle holds, right? Because if we write AC for the complement, this is a trivial thing to verify even for undergrads. So that's why this Hilbert accepted the law of excluded middle. Now, let me tell you why Brouwer didn't accept it. Because now what I want to do is that now I want to assume that classical logic is the logic of discrete spaces. When you work with sets, that means that your topology is discrete. And now I want to consider, not necessarily a discrete space, an arbitrary space. And now you have opens to work with. And when you work with opens, then again, you know, disjunction and conjunction are again going to be interpreted as union and intersection. And union of two opens is open, intersection of two opens is open, but now you have a problem with the complement, right? Because you take the complement of an open set, what you get is not open anymore. You got to open it. So you open it, and all of a sudden, you know, you lose your law of excluded middle. Here, a very simple example on real line, which is probably one of the go-to examples when you do anything. Pick 0, let make this A. Now, complement of A, and these are very simple calculations. That's going to be this closed interval 0 to infinity. But now you gotta open it. Now you gotta take the interior of this. And so you're opening this thing. And now this point 0 is not in A unit negation, because the negation is interior thing. Right? So very easy, you know, to kill the law of excluded middle if you look at it as from the perspective of topological space.
This is a reconstruction that you make of the reason they could have pushed power to reject, exclude the middle, or there are documents that show the browser or reason this way?
Coming up in a very interesting quote by Rasil and Sikorsky, that quote will answer your question. So the answer is that this is not what how Brouwer was thinking. But this is what's, so I'll get to that in 2 minutes. Okay, so now, the same way we can think of classical logic as the logic of power set algebras, we can think of intuitionistic logic as this as the logic of algebras of lattices of open sets. And we have the same way Stone represented Boolean algebras as this special power set algebras. You can represent same Stone a couple of years later represented every hiding algebra as an open set algebra. Every algebra you can embed in open set. And so so we can think of intuitionistic logic as the logic of topological spaces. So that gives really meaning to these Brouwer's ideas, right? Now it's, we're putting ourselves, it's a very good mathematical footing, right? That of topological spaces. Okay, now here's this quote from Rasil and Sikorsky, and you can see that this is what they call Brouwer's ideas. Vaguely defined philosophical ideas concerning the notion of existence. That's what Rasil and Sikorsky call Brouwer's ideas, right? Just very vague stuff. But it's amazing, they say, that this is what it comes to.
Very nice. Where you write it? Where does he write it?
Huh?
Where?
In their famous book, 1963, Mathematics of Meta-Mathematics, you read the introduction and you get to the Brouwer stuff and then you read this. So now, this is how intuitionistic logic connects to topology. Now we have this S4 that Gödel translated into intuitionistic logic. How does that relate to topology? Also very naturally, because in the very first course of topology, what do we teach our students? That you can define topology through open sets, or you can define topology through the interior operator. Defining topology through open sets, that's intuitionistic logic. Defining topology through the interior operator, that's S4. Because now what you're working with is no longer you're working with open sets, but you're working with the power set. And now it's your interior operator that's responsible, for this getting your fixed points, because opens are going to be the fixed points, right? And so it's exactly the fixed points of this interior operator that give you this lattice of open set. And so it is exactly these ideas that give us faithfulness of Gödel translation. Because now I'm going to forget this reading of box as necessity or as provability or anything like that. I'm going to read box as interior. And the corresponding diamond is going to be the closure. So from the semantic perspective, all I'm doing is that I'm doing topology. I'm taking the interior operator, that's what my box is. I'm taking diamond, that's what my closure is. And then intuitionistic implication is nothing more but the classical implication, but you have to open it. And this is exactly how now you can very easily prove this faithfulness of Gödel translation. Because if something is not provable in intuitionistic logic, it's going to be refuted in the opens of a topological space. But the same topological space also has the power set and its interior operator. And then the Gödel translation of this formula will be refuted in the very same topological space, but now read as the power set, with
Question?
Yes.
So you're saying box, the necessity is the interior and the diamond is enclosure. Can you give a little intuition for why or how to think about that?
Like, why should diamond be closure?
I don't, just maybe
Or why-
a way to think about it, why there would be a correspondence there.
I'm about to do Kripke semantics that's gonna give some different way of thinking about that, and maybe the two together will give you a slightly better idea how to think about that. Because what I'm gonna do now is that there's this famous Kripke semantics, and usually people first start with Kripke semantics and topological semantics is some kind of sideshow, but I want to reverse that. For me, topological semantics is primary, and Kripke semantics is just a special case of that. And so you're going to see very easily from Kripke semantics why blocks could be read as the corresponding, what interior is going to be in those Kripke.
So there is one thing that is not clear to me. When I read the box or diamond are modeling, they operate on propositions. What is possible or necessary is a proposition. When I read them as interior closure, are interior closure of what? So the sentential letter.
My sentences become subsets of my set. So my power set becomes.
So the box A.
Yeah, A is a subset. And box A, so here.
It's another subset.
So I define valuation from my propositional letters to the power set of my topological space. And now V of any P becomes an element here. And now the interior, and more generally, you can now calculate the interior of any formula to be, V of box to be the interior. So V of is a subset, and then you apply, and then the same with closure. So if you combine.
So this theorem is proved using the stone representation theorem you mentioned, or?
Good point. No, it's proved using purely algebraic machine. The way that they proved, right? So they proved it purely at the level of algebras. They wouldn't even go to topological spaces. They would talk about hiding algebras and closure and interior algebras. And everything they would do would be basically the same what we're doing more concretely here, but they would be at the abstract level of hiding algebras. Then you can represent every one of those as a set algebra and then do the same.
So they don't construct a topological space out of it.
They don't, but later authors did. But if you want to go back originally how they did it, it was at the level of hiding algebras.
Do we have a syntactic proof?
Very good point. So recently, some people found a syntactic proof in Gödel's notes, which were never published. So apparently, Gödel and Tarski talked about this in very early 40s. And I think that Gödel would have published his notes, but I think that Tarski told him that the result is true. And so from his perspective, there was nothing to publish. But in his notes, he has a syntactic proof. Now, that's back in the 40s, right? Now, since then, a lot of research was done, right? In the 1980s, the famous Harvey Friedman, together with Flagg, developed, this translation of intuitionist arithmetic into epistemic arithmetic. They had the syntactic translation. There's a long story, right? Then in the early 90s, someone found a mistake that their translation is not faithful. And then in the 2000s, there's a whole, line of research going in that direction, right? That there are syntactic translations, but if you want faithfulness, they are very, very complicated, and there's very involved proof theory to behind. While this is semantically very simple, and the level of ideas are very clear. Right? While these syntactic translations, the other translation from S4 to intuitionist log is very complicated. So if your proof theories, probably you want to read these Gödel's unpublished things, but if you're modal theorist, then you want to follow Tarski's way or more concrete. Any other questions, folks? Okay.
I have a question. The slides aren't showing to the people on Zoom.
Yeah.
Oh, that I don't know how to resolve.
What's the problem?
Okay, we're gonna look into it right now.
Thank you.
You are connected to Zoom, right?
I believe so. Yeah, go ahead and minimize it.
Okay. You were sharing. Yeah. You cannot see the slides?
No, I can see it now. Thank you very much.
Oh, okay.
Sorry about that.
Sorry.
Glad you said something. Yeah.
Okay, so like I said, for me, topological semantics is primary. Kripke semantics is secondary because it's just a special case. And how special is it? Oh, how do you get rid of this
Yeah.
one line here? Oh, there you
It
go.
appears.
Okay, thanks. No, that's good. That's good. You can just put it here. So this is related. So there was this famous Russian topologist Alexandrov, who's done a lot of work. Who's famous for many things. But one of the things that in topological circles he's less known for, but in logic circles he's very well known for, is this Alexander topologists that come from pre-ordered sets. A pre-order is a reflexive and transitive relation, and every such gives rise to a topology. You just take, if you have one of these pre-ordered sets, then you can look at all sets that are upward closed or upsets, or you can look at all sets that are downward closed or downset. They both give rise to topology. So the basic idea is this, that if X happens to be here and you move to another point, then that should stay in there. So they are upward closed. It's very easy to check that these things form a topology, but not just a topology, but a very special topology where each point has a least neighborhood. What would be your least neighborhood? You pick an arbitrary point here, and then the least neighborhood is exactly going to be the opposite, right? So this thing here is going to be the least open neighborhood. Equivalently, these are those topologies. For example, this real line is not such. These are exactly those topologies. Another characterization, in case you're curious, is that arbitrary intersection of open sets is again open. Right? That's a very unusual condition for topologies.
I'm sorry, what is the least neighbor for the point X? How do you build this little?
Yeah, like this. You look at all y's that X can see. So everything above X.
Thank you.
So from the order of the real line, you can construct one of those topologies.
Yeah.
It's not the standard one, right?
Yeah. So for example, take this and So once you start from a topological space, then you need to say what your order is, right? So that's the specialization order. You just say that you can start from an arbitrary topological space and then define what they call specialization order. You say that X is less than or equal to Y if and only if X belongs to the closure of Y. And suppose we start from R. Who can tell me what order that's going to be if I start from R?
Terminology.
Yeah, just identity, right? Because every point is closed, right? In any T1 space, this order is going to be just identity, right? So if I take this order, and if I take all upsets of this order, I'm not going to get R back. What I'm going to get back is the discrete topology on R. So these are very special topologies, and if you start from a good topological space, which is at least T1, then its specialization order always is going to be identity. And then the corresponding topology is going to be discrete, right? So it's not going to be very informative in that case, but it's very informative, to think about if you want to do Kripke semantics. That it's very informative to think about things like that. Okay, so what is next? Now this is going kind of backwards because people start Kripke semantics of intuitionistic logic by saying that we're going to interpret formulas as upward directed sets in a Kripke frame, right? And then the question is, why is that done? If you think topologically, that's because you want to work in the open subsets of a topological space. And in order to be open, that's exactly what it means to be an upset. So that's why, when you're interpreting intuitionistic logic in a Kripke frame, you have to work with an upset. It has to be an open set. And it is also clear why intuitionistic people who do critical semantics of intuitionistic logic, they don't work with pre-orders. They always work with partial orders. Why? Because there's no difference between pre-orders and partial orders from the perspective of taking these upward directed sets. They don't feel the difference. Pre-order is the one that can have these kind of things. But once you take an upset, it's going to swallow both, right? So if you have that, you might as well identify this into one point. And this identification topologically is a very well-known procedure known as T0 reflection, right? So really what's going on is that pre-orders are non-T0 topological spaces because you could have these things and then once you identify them, you get a T0 space, and that's exactly what this T0 reflection is from a more general topological perspective. Okay, and then in 1950s, people started, there were three major schools, you know, in this direction. You know, there was the Dutch school, of course, you know, and then there was this Japanese school. They are responsible for one of the representatives of the Japanese school, named Umezawa, in 1955, introduced, you know, this all logics, you know, that are situated between classical logic and intuitionistic logic. And you can think about it this way. So up here you have your classical logic. I will use CPC to denote classical logic. Down here you have IPC. It's much weaker than this. And then there's the whole bag of candy that you can have, right? And so each one of those you can think of as a principle. To get this, you're adding a principle or a bunch of principles that are classically valid, but intuitionistically not valid. And then, yeah, so that's another representative of Japanese school, Hosoi, you know, he said that that's how you can think about these things. And now what you can do is that now you can talk not only the fact that intuitionistic logic is translated into S4, but you can now pick any logic here, and you can also translate, you can talk about some modal logic above S4. And you can talk about the so-called modal companions, right? You say that a modal logic above S4, now here's another bag of candy. These are very big bags, by the way. These are,
Do you have at the top?
What you put in the top, exactly.
yeah, you can put, because I'm not putting, it depends whether I want to also put something on top, whether I want contradictory logic or not. If I don't put contradictory logic, then here I basically put something that is term equivalent to classical logic. When I say term equivalent, what I mean is that it's not exactly classical logic. It's really S4, but what I'm adding to it is that box does nothing. I say that box P is just P. So what that means is that this is really classical logic. And so that's what you put on. But now what's going to happen is that now you can ask, you know, once you start talking about modal companions, now you can ask question, whatever intermediate logic you pick, you can start asking how many modal companions it has. In particular, you can pick IPC, and you can ask the same question, how many modal companions does this have? And we can answer those questions. And I won't do the proofs, you know, but I'll tell you, you know, what the answers are. So in the language of modal companions, what McKinsey and Tarski proved is that S4 is a modal companion. So now, how do we explain what's happening? Why do we have this many modal companions? What is the semantic explanation? Right? So here's the semantic explanation of that. But the basic idea is this, that you pick some partially ordered set, say finite, you pick some partially ordered set. Now what you can do is that you can start blowing it up. How do you blow it up? you start turning these points into big clusters, right, that are all related to each other. So I'm turning my partial order into a pre-order. And I can blow this whichever way I want. So this blowing up is something that intuitionistic logic and intermediate logics don't feel. But it's something that modal logics do feel. And it's these different blowing ups that are going to be responsible for different logics here. And that's why when you blow this up, different logics can be, many different logics can be modal companions of the same logic. It's through these blow-ups. Now, among these blow-ups, there's no end to it, right? I mean, you can make this as big as you want, but there's always one privileged one, which is you just don't blow anything up. And that's exactly what's responsible to understanding. So this is my least modal companion, but it's this guy, when you don't blow anything up, that's responsible for the largest one. So now I'm going to change my picture a little bit, because I'm getting to the first major result, which was proven back in the 70s. So here's my S4. And now there's whole bunch. These are all my modal companions. So these are modal companions. Of IPC. And here's the largest one, which so happens to be the Grzegorczyk logic. So this is the logic that was introduced in 1960s by Grzegorczyk when he was trying to understand Cohen's continuum hypothesis solution, and how he was building, these models, where you can have this very crazy behavior of cardinals. Right? And so these forcing ideas were behind introducing this logic, and it so happens that Grzegorczyk's logic is exactly the logic of well-founded Kripke frames. And it's exactly, in the finite case, well-founded Kripke frames, pre-orders are exactly finite partial orders. And exactly because of that, you have that Grzegorczyk's logic is exactly the logic of these finite partial orders, and it's exactly the privileged one, because you are not blowing anything up. The models of Grzegorczyk are exactly the ones where no blow-up happens. So that's why of course, the real proof is more complicated, right? I'm just giving you an idea. But so that's how all these things happen. But now you can pick any logic here, and the exact same thing is going to happen. But here's going to be the least one that this gets translated. Here's going to be the largest one that it gets translated. This is denoted by tau L, and I'll just put it up in a second. This is going to be sigma L. And so these are the definitions. And so we have this complete control of these modal companions. They always form this interval from here to here, and these are the only ones that can be modal companions of a fixed logic. And what's important now is that this one has its own extensions here. And so we have this perfect match between these guys and these guys. Lattice isomorphism.
This is a question that I wanted to ask you also. What do you prove is the existence of the rejection, or you identify the rejection?
Yeah.
That is, do you have an explicit algorithm for the translation or not?
Yes, it's sigma. Sigma is the bijection, right? This sigma from the extensions of IPC to normal extensions of Grzegorczyk's logic, which does the following. You give me a logic L, then what I do is that I take Grzegorczyk and I add to it all the translations of all the formulas in here.
And that's Gödel's translation.
That's Gödel's translation. That's Gödel's translation. So it's effective.
So the sigma L is characterized by all these red bubbles having only one
Yeah, just
Is that
nothing.
right?
Yeah, just.
And the tall L,
the
does it
width,
have a characterization in terms
Tau?
of these trees? Yeah.
all positive.
Oh,
All
everything.
positive.
Okay.
Everything.
Mhm.
Everything there is in the whole life. So that's this. That's a good point. You know, that you can allow everything that can be allowed. You allow nothing.
Mhm.
So that's how nicely and beautifully. Now, by the way, this is a hard theorem to prove. I'm making it look easy, but it's a very hard theorem to prove. Here's a rough idea how you prove it. Especially those who like universal algebra and who, instead of working with logics, will work with the corresponding varieties. Really, what's happening is that what is amazing, that whatever variety of Grzegorczyk algebras you pick, inside that variety, there is going to be the class, subclass, that comes from the corresponding intuitionist, from the corresponding variety of hiding algebras. And what you need to prove is that this class always generates the whole variety. And that's hard to prove. There's this famous Blok's lemma that allows you to do that. We can talk more about this afterwards, you know, but that's really what's behind it. And in terms of logic, it's really this, you know, that modals of L, those are all say algebraic models. They are all of those, or you can think in terms of Kripke if you prefer, you know. And then there should be representative. So these ones that are coming from intuitionistic world, the ambassadors of intuitionism, they should generate.
I have a question. How do you know that this picture on the left-hand side is complete? I mean, I think there will be countably many intermediate laws, right?
No,
Each one
uncountable.
uncountably many, even intermediate laws.
Mhm.
But we know that there are uncountably many laws, but even intermediate.
Even
laws,
intermediate.
but if they are defined by adding formulas, and the
Sets of
collection of formulas are sets of formulas,
Sets of-
no, not uniform.
Yeah.
Right, that's right.
Yeah.
And then how do I know it's complete? How do I know there's this? It's not any new kind of a new set of axioms missing that somebody forgot to put there.
But by definition, you cannot miss them, right? Because you're looking at every L looks like this. IPC plus some set A of formulas such that every member of A is provable in here.
Yeah.
So by definition, you know, it's one of
Finite.
everyone here.
Finite set, right?
No.
Even infinite set?
Yeah, because otherwise, if it's only finite, you only
Yeah,
pick up
yeah.
countable many. But there's uncountably many of such. So
So it's complete by definition, I see.
remember, we have cardinality restriction.
Yes,
We
yes.
cannot be more than uncountable, but we're exactly under.
But the hard part of that theorem is that you actually do get an uncountable set.
That's the hard part.
We know the upper bound, that's easy. But the fact that it's actually realized, it's not so easy.
Yeah.
That's actually what made Yankov famous. You know, Yankov formulas. If you heard about Yankov formulas, these were designed specifically for that purpose. And so that was this hard result in 1968. And if those of you who are algebraists, you know, this is really the splitting technique, you know, that allows you to prove it. Well,
Blok-Esakia theorem, but did they do it independently?
independently, but the same year. 1976 was the year. Blok didn't know about the existence of Esakia. Esakia knew about the existence of Blok, but he didn't know that Blok was proving the same thing, right? So he was completely independently. Blok in his PhD, which was never published, and Esakia in a conference proceedings, which was also published only as a note.
Is it the same proof? Because I know
No.
algebraic proof of Blok-Esakia.
No, the proof is also different, right? Esakia was mostly working with what we now call Esakia spaces, right? So his proof was dual. And we can talk about the details. So,
Is that why he developed Esakia
Yeah.
duality?
yes. In fact, he developed Esakia duality for hiding algebras by first developing Esakia duality for closure, these S4 algebras, and then realizing that if you identify clusters, what you get is going to be exactly the dual spaces. People forgot that. They called that UC and Tarski duality, but they call what was byproduct of Esakia duality. Now, history plays funny. It's how it works. It's funny. Yes.
So then you just say that there is this isomorphism between the intermediate logics and this, let's call it the fiber of the Greek logics. What about other fibers?
Very good question. So for example, this one will be bigger. So you could have this one. By the way, Marco was asking me to put S5 somewhere on the picture. So I'm about, Marco, you're going to be a happy man now. There's your S5. So this one has its own fiber. So these are all modal companions of classical logic. These are all modal companions. And now there's going to be this big fiber. This is not isomorphic. No, but you can single out the ones, because you can have this infinite behavior with still some restrictions. So there can be many things, and then when there's absolutely no restriction, it's only the tau L's that are going to be isomorphic to them. But there are more than just tau L's.
Tau is.
Yeah, tau L is basically, tau is built this way. Instead of Grzegorczyk, I'm doing S4, but then the rest is the same. So the only difference is that and this is something that's pretty remarkable, right? Because people were looking at this sigma, but even before Blok-Esakia, they never realized that sigma can be so simply obtained from tau by simply demanding Grzegorczyk. And of course, semantic explanation is that you're not allowed to do any blowing. It's really what it is. Are there any other questions? Should we move on? Because now all hell's gonna break loose, right? All these beautiful answers gonna be out the window. Are we ready for that?
So maybe one more question, like this thing with the fibers which have one or two or more elements. Is that something that comes out of Esakia duality then?
Esakia duality, but for S4, right? Not for hiding, right? Because hiding is not gonna fill this at all.
Mm-hmm.
But yeah, from S4 you're gonna fill this. And there's this famous Damet-Lemon conjecture that was open for many years, which said that if some L here is cryptic complete, is this tau L also going to be cryptic complete? Mm-hmm. And that's exactly how you prove this conjecture, that you're putting, these arbitrary blow-ups here, right? And that's really what you need to prove, is that tau L will be exactly axiomatized, complete with respect to these arbitrary blow-ups. Right? That's not easy to do. Esakia tried and he couldn't prove. It was until Zakharyachev developed his machinery, it was untouchable.
Oh, this is one thing Zakharyachev.
That's why Zakharyachev developed his technique, exactly to prove this Damet-Lemon conjecture.
Sorry, in this graphic, of course, if you look on the left part, there is a sense in this classical propositional calculus maximum. You say that, and you think that is not contradictory. So which is the corresponding sense in which S5 is maximum?
S5 is, it's the largest modal, not just maximum, but the largest modal companion of classical logic. But it has extensions.
But it's not maximal with respect to classical logic.
No, it's not. It's not maximal, because I'll tell you why. Semantically, it's easy to see, because you can think of S5 as the logic of equivalence relations. So you take one big infinite cluster, and then that's an equivalence relation, and that's S5 is the logic of that. But there will be extensions, because you could say that I have exactly n many points in my domain. You can express that with a formula easily. Exactly n points in the domain. So these will be proper extensions of S5. And so there's countably many of them. And so it's not, this is the maximal one, because after that, there will be just contradicted. Nothing else. But it's this
and that's
one.
because that's the one that says that necessity means nothing.
Yeah, that tells you that in here you only have 1 point, nothing more. But you could have 2, you could have 3, you could have 4, you could have infinitely more. And this exactly measures how many points you have is exactly what. So you can describe exactly what the extensions are. It's a decreasing chain. This one is the logic of 1 point. This one is the logic of 2 points. This one is the logic of 3 points in a cluster. And then this is the logic of as many as you want.
Do we have descriptions of the lattice of model companions of other logics?
Do we have what?
Descriptions of the lattice of model companions of some other logic, for example, IPC.
Yeah, so this is continuing. Bad things happen. but you gotta take it with positive perspective. This is not a bad thing, it's a feature. It's a feature of this thing. The reason is that, again, the splitting technique will produce continuum. And in fact, you can put some structure on this. I won't talk about it in much detail, but you can put some structure on it by measuring the depth of your your algebras, and then starting from depth 3, you already have continuum. So it's very quickly, the complexity becomes very hard to control. But that's why this is a nice result, because it provides some kind of structure. You're using intermediate logics to put some structure into this more complex world of model logics. That's how you should think about this. At least that's how I think.
So you think of intuitionistic logic as a tool to investigate model logics?
If I tell this Brouwer, he's gonna shoot me, Good thing he's dead, so he cannot shoot me. But for me, it's a tool, right? Because it's a much less expressive language. And so that's exactly, so it allows you to put some equivalence relation on the more expressive language. And it allows you to classify things in a compact and convenient way. That's one way of thinking. I'm not saying that that's necessarily all the way. But it does that, among other things. So now, the whole problem now becomes that it's very natural for logicians.
No, sorry. Another thing before we go to the mystery. So this is very nice from the point of view of the description of the situation. It has also, I suppose, yes, but I don't know, perhaps not. It has also an interest from the point of view of proofs. That is, I can use proofs in one domain to come back and prove on the other domain. So it has also an heuristic.
That's a very good point. And if you want to develop this proof, going from proofs in intuitionistic logic to proofs in S4 is easy. That's the easy part. It's going back that's very difficult. When you have proofs in S4, can you translate them into proofs of the corresponding modal companion, right? And that's where, what Jose was talking about earlier comes into play. What is the proof theory? How can you translate backwards, right? And there are tools, that do it, but the proof theory becomes complicated. Okay. But it's a very good point. That's exactly what Harvey Friedman wanted, back in the 80s. So, and then you just, pinpointed why he wanted exactly for that reason.
Okay. Let's go to the predicate case.
It's going to be bad.
That is a mess.
Well, first good news, right? That Gödel translation extends very naturally. But I want you to notice non-symmetry up there already. That universal quantification is very different from existential quantification. So this is the feature of intuitionistic logic. We have these are non-symmetric things, right? And so you cannot apply the symmetric machinery, to get results. But one good thing is that this still works. The reason it works is that we're lucky that Kripke semantics works in this case.
Sorry, it's always true that on the left we have intuitionistic quantifier, on the right we have classical quantifier.
Yes. Everything on the right is classical. Everything on the left is intuitionistic. So from the classical perspective, these are not symmetric. They're not definable from each other. But already here, we have problems, right? Already when you go to predicate Grzegorczyk, there are many things we don't know. I was doing some research into literature recently, and well, first of all, I'll get to that slide in a little bit, but there are unverified claims all over the place. Right now, I can give you in 5 minutes 3 or 4 open problems that remain open to this day. Right? And people thought that they proved those, but they are open, and I'll tell you why. So First of all, first bad news about predicate Grzegorczyk is that we lose Kripke completeness. So, and in general, this is one of the, in my opinion, the largest problem into understanding predicate logics is that we do not have adequate semantics. We simply don't, right? So, people try Kripke semantics that didn't work. What is the next thing? Now you go to shift semantics, right? So you start working with shifts, right? That's a very natural thing to do. Well, again, it works well for some specific systems, but it doesn't give you these general completeness results. And so then the question becomes, what can we do? Well, you can do these hyper doctrines or whatever people in category theory call those things, but these are very hard to work. They don't allow you the same type of modal theory, because just having modal theory is not enough. You need to have a modal theory that you can work with. And these hyper doctrines are highly difficult objects to work. So that's the major problem. And so here are these unverified claims that I recently confirmed with several people. And all difficulties go back to Harvey Friedman, that his syntactic, these proof theoretical tools, they are very nice when they work, but they never realized that what they described was not actually faithful. So then it turned out to not to be faithful. Then all these claims that predicate Grzegorczyk is a modal companion of predicate intuitionistic logic, they were made, this paper 1989 essentially used flag Friedman. So that's out the window now, right? And then this other paper by Naumov also used flag Friedman. I now have a proof that what Naumov wanted to prove is not proven. I don't have the same proof for Pankratiev. I think that predicate Grzegorczyk is still a modal companion of intuitionistic predicate logic, but we don't have tools. See, the problem is to design the right tools. You cannot use Kripke semantics. Maybe we can use shift semantics. Maybe we can use some kind of hyper doctrine semantics. But
Can you say again why you can't use Kripke semantics?
because IQC is complete about all Kripke frames. In particular, you have to use ascending chain. Kripke frames that have ascending chains. And Grzegorczyk doesn't like that. Grzegorczyk says that I'm well-founded. I cannot have ascending chains. So you have to do something, right? You have to prove completeness with respect to, and then Kripke frames are not enough, because once you put restriction on height, once you say that I don't allow ascending chains, extra formulas will be valid. So intuitionistic predicate logic is not complete with respect to Kripke frames where you don't allow ascending chains.
So you have a really big problem there.
Yeah, you got a well, I have some ideas about that, right? But they are not verified, right? So it's an interesting problem. Well, I guess what I'm trying to say is that if someone is curious about those things and likes those things, here are some very interesting open problems. Anyway, I'm gonna resolve this now. I'll stop as soon as I can. I'm gonna resolve this by taming predicate logic and by only allowing fragments, right? And then so usually this even goes back to Friedman and also Van Benten. They were saying that you got to work with fragments. This whole predicate logic, it's not even decidable. It's just too much, that to work with, right? Because you're not going to hope for good results, although that's debatable, right? Tarski would say that that's very debatable, right? But one way or another, I want to look at fragments, right? And then all of this now is going to be put in the right perspective if you concentrate. Yeah, so this is my way out. And this way out actually goes back to this famous philosopher Pryor, right? Pryor was the first, in the 50s, who said that, well, let's see if we can work with some small fragment, maybe even just one variable. Now, the whole Aristotelian syllogism, all that it requires is one variable. It doesn't require more, just one variable. You allow one variable and quantification, and you are going to get pretty good expressive power. So then people, started to study this.
What do you mean by fixed variable?
I want to allow only one x. Not only I have monadic predicates, but I don't want to allow y.
I understand, but why fixed? One fixed variable, what is the difference between one fixed variable and one variable?
Here, the difference.
The variable is always the same in any formula?
Yeah, so I don't want to allow this. So I don't want to allow something like this, that I have p X and then also write Py. I don't want to allow this. So I only can work with one variable X.
So you
So
don't
this-
allow substitution, right?
Yeah, I'm not allowing.
Yeah.
Yeah, but
And the reason that I'm doing this, because I will only be allowed to do this. And then I can erase this X and view this as a modality. Because if I allow also Y, I'm not going to be able to do that. But if I only allow X, then basically my quantification becomes S5 type of quantification, and I'm going back.
I understand. Still,
prob-
I'm not understanding which sense that this variable is fixed.
I don't think that's important. I mean, it's just.
I think that
One-
fixed
one
is
identified
with one variable.
One
Yeah.
identified
With a-
variable
okay.
which is going to be called X.
Okay, that's call what you want.
Yeah.
Yes.
Yeah, okay.
Okay.
Because what that does is that now, I'm gonna replace this predicate S4 with actually a propositional modal system, which is gonna have predicate S4 has box, and then it has for all X. And now I'm gonna replace for all X with just S5. This is an S4 modality. And this is an S5 modality. And so now I'm back in propositional case, not unimodal, multimodal, but still proposition. And I can still handle things using the machinery, say universal algebra. So I'm replacing predicate
I'm
logic.
already see it is a trick.
It's a trick.
You eliminate the predicative quantifier by predicative.
Well, but for example,
logic.
back in the old day, Weisberg, for example, proved that S5 is nothing more but one variable fragment of classical logic. So if you want to work in if you want to do Aristotelian syllogism, you never have to go past S5. S5 is good enough. And I'm saying the same thing now, right? That I'm doing Weisberg trick. If you're okay with Weisberg trick, you should be okay with it.
Okay.
Yes.
This is Arthur Pryor. Time, tense, and modality.
Yes,
are different.
that guy. That guy. And if you open that book, 1957 book, somewhere down chapter 9, or I don't remember exactly now, he talks about fixed and variable, and he talks that this is this MIPC, modalized intuitionistic propositional calculus. That's what this stands for. So that's his, and then I changed. Now I call, instead of modalized, I call it monadic. So it's same word M, right? So that's what that stands. That's Pryor's system, and it was, I think he was his student, Boole, Richard Boole, I believe, who in 1966 proved, that. So that he proved, that Pryor's axiomatization was faithful. So, the same way Weisberg proved that S5 is the one variable fragment of classical logic. And so then what I get, I want to go fast now, yeah, right? So then what you get is that now you just work with so-called augmented Kripke frames, right? Now you're adding an equivalence relation, and you have this equivalence relation to model your quantification. Now you have less than or equal to model your box or diamond, and you have E now to model your A or its corresponding E. And now we have this nice connection with Kripke bundles. These are these Alexandrov, bundles. The topological bundles play an important role in many different areas of mathematics in general and topology in particular. Now, assume that you are doing, in particular, shifts are those bundles that are local homeomorphisms, right? So now what I'm doing the same, but I'm doing bundles not of arbitrary topological spaces, but the ones that come from Alexandrov spaces. Right? That's what these Kripke bundles are. And so basically what I'm doing is that I'm now slicing up. Instead of working with pre-orders, I'm working with pairs of pre-orders. That's what these bundles are. And I have complete equivalence of the corresponding categories. So if you like bundles, local homeomorphisms, then this is the way you can think about it. And here's how you can handle this, how you evaluate things. For diamond, you use less than or equal to, and for E, you use this equivalence relation, existential. But here comes the key now, right? That what was the key why this Blok-Esakia theorem and Esakia theorem and these things worked because there was this nice harmony between two semantics. But this is the main message of today, that although you can fix things, the harmony breaks down. So now, because of universal quantification, the intuitionistic Kripke frames, it's our relation that is responsible for universal quantification, while in the classical logic, this bimodal S4, S5, it's equivalence relation. So basically, R is a quasi-order. Quasi-order is responsible for universal quantification. And it's only an equivalence relation is responsible for classical. And so P-morphisms are different, right? Even though at the object level, you're working on the surface with the same object, it's at the level of categories, at the level of morphisms, you do not have the same words anymore. And so we can prove now the Blok-Esakia theorem fails for exactly that reason. And we can prove that also Esakia's theorem, that there's the largest modal companion, fails. So then, and I'm skipping the details, right? So now we come to the last bit, of the talk, that how are we going to, is there a way to fix that? Is there a way to get our harmony back? Maybe it's intuitionistic logic, the way that we axiomatized it, is not enough. Maybe we should look at some extensions. That was the basic idea that Esakia had. And I learned from Marco that Ettore Casari was on his committee. So this is the year when he passed away. So we come to later. Yeah. Did you know him?
No, I never met him.
You never heard the name?
Yes, I heard the name, but I never
heard the
met
name. Well, it's his scheme, axiom scheme, that all of a sudden gives us our harmony back. So here's the formula. Those of you who are familiar with Grzegorczyk's axiom gonna see a lot of connections.
Mm-hmm.
This is the formula that actually, basically, if you replace box with universal quantification, what you get is Grzegorczyk. And that's not an accident.
Very nice.
And here's a law that Esakia came up with, because we usually have generalization. If P, then for all XP, right? But instead of generalization, you have this modified generalization. So since we have philosophers in the room, my hope is that they can actually think about how to think about it. So what is it that, so this is not provable intuitionism. So what is so special about it? And this is exactly the right axiom in terms of Kripke semantics, because it's not going to allow ascending chains. So here are some positive results. That we get our Esakia's theorem back when we go to the Casari, when we work with Casari. Yes, back. To
the formula.
There you go.
So the first x is bounded by the first quantifier. Okay. And the second x is bounded by which quantifier? By the one that is close to it, but also there. So how can I distinguish? I have only one variable. What is the scope of the quantifier?
Yeah, you can write y in there if you want to.
Sorry?
You can, in here, you can put y if you want to.
Ah, okay.
You can if you
Then
want
the third one is a z.
If you want to, yes. Because these are all bounded, it doesn't matter which one.
Okay.
But I wanted to do this with one variable because I made this big speech of working with one variable, right? So I wanted to be
then you make one variable,
you bring in the y and the z. Yeah, I didn't want to go there, but
It's fixed in your variable.
Don't put me on the spot.
So it's one or more fixed variable.
No, I mean,
No,
the
I
whole
know.
point is that you can, if you want to, Anyway, so this probability interpretation and then the whole this Solovay business, that it all goes through here, right? So what happens, let me tell you what happens. That usually you have this very nice situation that intuitionistic logic, IPC, gets translated into Grzegorczyk by Gödel translation, and this further gets translated into Gödel-Lopes probability logic, and eventually all these talk about probability and piano arithmetic. And so you can try to extend that to monadic case. So now I put MIPC here. Then I again embed this into M. Grzegorczyk, no problem. Here, things go bad. So this breaks down. And that's, you can think that this is responsible for also these negative results, why Blok-Esakia fails and why Esakia's theorem fails. But here's the positive things is that if I put plus here, if I go to these Khazari versions, then my life gets good. So now I'm good here. So this is the right generalization of Sullivan. So we're home then, right? So this gives you a lot of evidence that there's something about Khazari. And some people would even go as far as say that the real intuitionistic predicate logic should be the one that is not the one that we work with, but the one that should be obtained by adding the Khazari formula. And when I told Trulstra that, he looked at me funny and said, leave intuitionistic logic alone. Those were his words, before he retired. I was, attending his last class, before he retired. And that was his words to me. Leave the predicate intuitionistic logic alone. But I think that there's.
Did he want to protect the logic, or did he want to protect you?
I don't know. That I cannot answer, and he cannot either because he's not alive anymore. Right? So, but one way or another, there's a lot of evidence that we should think about this, right?
But Khazari did not propose this for your reason.
No,
He had a philosophical reason.
yes,
Right. So
I don't know what it is. I was
I think,
hoping
I
that
think we
Marco
should.
would.
I think we should look into what that is, right?
Yeah. Yeah. To this day, I don't know. By the way, so there are many things around there that it's very hard to find in the literature. Very hard to find.
It has a flavor of omega consistency.
Mm-hmm.
A flavor of omega consistency. It's just my intuition. Right? No arguments, just my idea.
Maybe.
Mhm.
But this is, this is really what I think should be done, right? We should really look into what is this principle all about and what it's offering us, right? Because the same way, if you go back in history to the 70s, it was McKinsey, Tarski never went past S4, right? But now we have all this evidence that it's really Grzegorczyk that goes hand in hand with IPC. And so if you want to go hand in hand with these things and continue your journey on to piano arithmetic and those things, I think that you have to go past. You have to work with the Khazari scheme. That's what my work in this direction suggests, and not just mine, also Esakia's.
So did you learn this Khazari principle from Esakia?
I learned it from Esakia. When
And so you don't know like how he found it, or
how Esakia found it?
Yeah.
I don't know. I don't know. Khazari had in very early 80s, he gave a course on intermediate logics at Siena. Mm-hmm. And there are these, I've never seen these notes, but they exist apparently. So maybe Marco knows something, so, but I think that formula was fun. If you read, this ONOS 1987 survey of intermediate predicate logics and then intuitionistic modal logics, you'll see he references these notes, right? But I've never seen them. Mm-hmm. But apparently they exist somewhere.
So would Ono maybe Ono has a copy?
Maybe, but he's been retired long.
I know. Ono,
Hiroakira Ono. He was one of the prominent. Remember, I told you there were three main schools of this thing: Dutch, Soviet, and Japanese. And so Ono was an important representative of the Japanese school. And he was the one who also did some work in this direction, especially on this monadic intuitionistic propositional logics. It was interesting.
But I'm in contact with a study Florence in Siena last week for this note. Magari, for example.
Magari hasn't been alive for a very.
Yes. Perhaps he knows, but
We could ask Claudio Pitzer from Siena. Very possibly he knows.
Maybe. I mean, who else is in Siena right now? Isn't it Minari? Minari. Do you know him?
No, Magari, yes, but
I
Minari
don't know.
not very well.
I think he's in Siena. I'm not sure.
I think that he's in Florence.
Maybe he's in Florence. Maybe.
In any case, there are a bunch of people there, which is possible to ask.
Yeah, there's probably some historical reasons that he gives, some philosophical reasons he gives why one should work with that principle.
Yeah. It would be interesting to know.
Interesting to see, but more generally, I don't think that there will be much more than these principles, right? But understanding the principle and understanding modal theory of the principle, I think is important in this direction, because I think that it's going to give some insight into these negative results and how to resolve them. Yes,
Also, your friend Pitzer should know something.
Pitzer should know, or Daniele Mundici, one of them.
Daniele
Mundici, okay. Go ahead.
So everything is solved though, there's no problem?
No, everything is not solved. No, for example, Blok-Esakia, I mean, right there, see, these are all open problems. Blok-Esakia for Khazari's logic is still pending. I can prove that Esakia's theorem, which is that monadic Grzegorczyk plus is the largest modal companion of MIPC plus. But these isomorphisms, here's a simpler open problem. Every intermediate logic has a modal companion, a whole bunch of them. Does every monadic logic has a modal companion? It remains open to this day. And the reason that remains open to this day is because of this lack of correspondence in semantics. Right? Semantically, things break down. There's no harmony semantic. So Pancratian was the one of the guys who claimed that it is, but his proof doesn't hold because he used flat Friedman, which is not faithful. Right? He didn't know at the time. And then everything that you translate, this is only for monadic. If you go to the full predicate, everything is open.
So you hope that in the end it's going to be harmonic? You
In
will
the
find the
monadic case,
harmony?
I can tell you exactly what the problem is topologically. Topologically, the problem is that in the monadic setting, you need E saturation of Kloppen to be Kloppen. All you can get out of intuitions is that E saturation of Kloppen absence. And E saturation of Kloppen may not be Kloppen. So what you need is Blok type of lemma that will tell you that look only at those models where E saturation of Kloppen absent is Kloppen, and then you need to prove that those are enough.
Yeah.
So there's a heavy-duty theorem that I believe is going to be true if you go to Khazari, but I don't think that it's going to be true. I mean, we know that Blok-Esakia fails,
Yeah.
but I believe that it's going to be true if you go to Khazari. So that's roughly what's going on in this direction. I hope you enjoyed it, guys. I'm happy to answer whatever questions. Thank you.
Very nice.